0.6 continuity, and I lost the track of days and parts. So we will discuss what it means for function to be continuous, globally continuous, piecewise continuous, continuous at the point, and why is that important. So let's start first with the basic notion. So most people would consider a continuous function one that you can draw in a continuous stroke without lifting the pen off of the paper. And for the most part, that would be correct. However, there are functions that that are continuous, but you have to lift the pen to draw them because you draw alternate pieces of it. Those are usually studied in analysis later on, so they're not going to pop up here. So for all practical purposes, we could think for now that any function that you can draw without lifting the pen would be continuous function. So you're thinking about sine x maybe, which is a continuous wave from negative infinity to positive infinity. And then you think of tangent, which is interrupted at pi over 2, 3 pi over 2, 5 pi over 2, and so on. You might also think on a function y equals x, which is a 45-degree straight line through origin. And then you think of 1 over x, which has those two separate pieces. So continuity is going to be this unbroken line, let's say. So if I take a look at y equals x, that's continuous. And if I take a look at 1 over x, it's discontinuous. And it's discontinuous at 0 because the left and right piece is not connected at 0. So now when you're looking at these two lines, the one on the left is continuous, is globally continuous. And the one on the right is globally discontinuous, but it has two continuous pieces. So it's piecewise continuous, actually. So we have to be kind of careful with all of these vocabulary and words. So this one is globally continuous. And this one is discontinuous at x equals 0. So this is our 1 over x, and this is just y equal x. So the way we're going to think and define all of this is we are going to define a continuity at a point, and then once we understand continuity at the point, we will build this global continuity formula. So we first start with this definition. We say that the function f of x is continuous at x equals a. Now I'm just going to put in parentheses at a point if, number one, f of a exists, number two, limit of f of x as x goes to a exists, and finally, if the limit x goes to a of f of x is equal to f of a. So this is what you're going to be using to check if the function is continuous at the point. And then later, once we deal with this, we are going to say that function is globally continuous if it's continuous at every point in its domain. So let's first work on on these concepts here. The meaning of the first line there is f of a exists. So this technically says that the point that you are looking at has to exist. So if f of a exists, then you can go on with the rest of the calculations. The second one says that the limit at that point, see x goes to a, the limit needs to exist. Now when you say that the limit exists at the point, that means that there is this neighborhood around it that had values that point to the limit, right? So it's a little bit wider statement than just figuring out a single point with the second line, because the second line uses the limit, and we know that limit uses all of the infinity of the points close to the value you're looking at. And then finally, number 3 says that the first and the second have to be the same. So now let's draw some graphs and understand how all of this fits together. So first of all, we know that if the function is perfectly continuous, f of x, you pick any point anywhere. So let's say this is your x equals a point that you were considering. You see that the y value for it exists. It's this is your f of a. So this point here has coordinates a, f of a. And you see that everything works for it. You see that right where the black dot is, where the point is, you see that the function exists there, and you see that the limit exists and is there, and you see that they're the same value. So I would say that the function is continuous at a right there. As soon as we start breaking anything of these rules, you will get the discontinuous function. So let's take a look at this example. So which rule is broken? Out of 3 rules that you have over there, which rule is broken with the graph on the bottom? The first rule. You see that f of a does not exist. Clearly, a is there, right? On the x-axis, you always have a. But f of a does not exist. And because f of a does not exist, well, you can't have the continuity because the point is not there, right? It will be like a section of the bridge is missing. Think about that, right? You have a cliff and another cliff over here, and a section of the bridge is missing right there. So that's like, okay, there's no point there. So this continues. Great. How about this one? See, as soon as I draw a black dot, what do you know?
1 is true.
The 1 is true, right? Immediately you know 1 is true. What now? Yes. 2 is not true now. Why is 2 not true? Yes. And this is the crucial part that you guys have to learn in this class. Limit from the left gives you one value. Limit from the right gives you a different value. If they don't agree, the overall limit does not exist, and that violates the rule 2 on our list. And now, by process of elimination, let's come up with something that will violate rule 3, but pass first 2 rules. Do we have function value? Yes, we do. It's right here. AF of A. So it exists. Do we have a limit? Yeah, we do. It's right here. From the left, from the right, it's whatever this empty dot is. And we see how rule 3 fails because they're not the same value. So these are the three ways in which you can ruin continuity. Either function value does not exist, or the limit does not exist, or they both exist but they're not the same value. Any one of those will create discontinuous function, in which case, right, you have the interruption right there. Over here you have what we call jump discontinuity, and then over here we have another discontinuity. This is called the removal discontinuity because you can actually stuff this back in and then fix it. So these are the three types of situations where you might have a discontinuous function. But as I said before, you might have a discontinuous function, but the other pieces might be continuous. Going back to our 1 over x graph, where we realize that this piece here is perfectly continuous. This piece is perfectly continuous. So I can restrict the domain and say from negative infinity to 0, I have a continuous function. And then from 0 to positive infinity, I have a continuous function. But between the negative infinity and positive infinity, the function is discontinuous because there is a vertical asymptote at 0. So these are some things that you need to worry about as you move along. Now, the best examples over here would be obviously piecewise functions, because we want to know whether those functions fit together or not. Also, the cool part is to kind of patch and fix functions to find what you need to do to a function to make it a continuous function. So let's take a look at some of those. So let's see, problem 18 looks awesome. It tells you a lot about problem 18 already, right? It's a piecewise function. The top piece is x squared minus 4x plus 3 divided by x minus 3 if x is different than 3, and it's 2 if x is equal to 3. So what do you think, looking at this function, what would be the natural place to look for the continuity? What would be the natural place to look for continuity? At which x value? 3. Because looking at the top part, right, of the function, it seems that there should be an asymptote at x minus 3, right, at 3. So if there's going to be any issues with this function, it should be at 3. So we just need to check and make sure that everything is okay at 3. So we are going to do continuity at the point, what point? X equals to 3. So let's go. Now, how do you do this? Rules 1, 2, 3. Compute those. So rule 1 says f of a exists. Is that true? How much is f of 3? It's 2. Awesome. So if x is equal to 3, f of x is equal to 2. So it passes the first rule. Great. Second rule says limit as x goes to 3 of f of x exists. Is this one true? How do we show this one? Yes. Yeah, but we are going to do the limit, right? So limit x goes to 3, and then you said you want to factor the top. Well, let's write it one more time. Factor, cancel, and the limit turns out to be 2. So limit exists. And then for rule 3, 2 equals 2 passes that as well. So pass all 3. So f of x is continuous at x equals to 3. So we have a function. We have no clue how the graph looks like. Apparently no one cared because we can compute these things without looking at the graph this time around. So f of a exists in your notation for the piecewise function. You have 2 pieces, and you just perform operations. So does f of a exist? Yes, that's the second line, because you can see if you plug in 3, if x is 3, then the function value f is 2. So f of 3 is 2. Awesome. Second part is the limit. You find the limit, and then you go from there. Now the problem with this textbook is that all of the problems are the same. They're all identical, you just have different polynomials. So I should probably steal Larsson book for a second, since I know it exists, and try to find a more interesting example to solve without me making it up. Awesome. So you open this book and it says f of x is piecewise function tangent of pi x over 4 and then x. All right. You immediately know what's up. Quickly. Let's take a look first at some cheaper stuff. Okay, try this one on your own to run all 3 rules. Rule number 1, rule number 2, rule number 3. What's the final verdict for the problem? Continuous or not continuous? Continuous? Good. So all 5 of you in the classroom are agreeing on that one. Excellent. Well, I have a classroom of 5. So let's take a look at this problem together. We have to first figure out value for f of a exists, right? That's the first one. Well, where do we figure it out? We figure it out on this line because this is the line where you have x equals to 1. The line on top does not have equal to 1. So you can't compute x equals to 1 on a top line. You must be computing it on a bottom line because that's where x is equal to 1. Yes, it's greater as well, but equal to 1 lives there. So f of 1 is 1 squared, which is 1. Exists, so it passes the first one. Second one is the limit. So limit as x approaches 1 of our function. Well, our function is piecewise function that contains 2 functions. And if you understand the piecewise graphs, which is what we did on the first day, you know that at 1 there is the divider, and then there is a function to the left and the function to the right, which are different functions, but we have one-sided limits, which means that this one now breaks into 2 different problems. Limit x approaching 1 from the left and limit x approaching 1 from the right. On the left, we have negative 2x plus 3 as a function. On the right, we have x squared as a function. So we compute these 2 limits. If they agree, overall limit exists. If they disagree, overall limit doesn't exist. It fails on the second one and continuity out of window. So plug in 1 on top because, again, nothing weird is happening. We have 3 minus 1, we get 1. 3 minus 2 is 1. And then on the bottom, 1 squared is 1. Since both of these agree, we know that the overall limit by the theorem from before, that the overall limit of f of x is 1, which means exists and passes. Third one is always easy because 1 equals 1. That means that the limit is the same as the function. So that one checks out as well. Since all 3 check, function is continuous. Function f of x is continuous. So these are the instances when you have to check a single point, because that one point could potentially ruin the continuity. Now, since you all love trig so much. I got 6 smiles on that one. Even though I said I had only 5 students on the previous problem. The stream is completely confused now. It's like if you haven't been in a class while the stream was going on, you have no clue what's happening, because I just said all 5 students agreed, and now I said 6 students smiled, which makes no sense. There are more than 6 students in the class. They just don't participate. That was only for the stream. You'll know what I say if you go and watch it. So which one should we do, 49 or 50, since you love trigs so much? 50? Well, you picked 50. It has cosecant. Pi x over 6. Nothing to worry about, as you can see. Now, here's the wonderful limit over here, the region. It says x minus absolute value x minus 3 less equal than 2. And it's 2 for x minus 3 larger than 2. Good luck. And remember, at all times, you picked the problem. Just get Larson book, okay? You will have no issues in life. Oh, maybe, oh no, I want to do one more. I'll do 58 after this. So how about you graph this first? No calculator, obviously. So, This is pink. So how's the graphing going? Like, you're not even freaking out yet with the absolute value of x minus 3. You're now just, right, worrying about the cosecant first. Like, we'll see where we have to cut it. Just how to draw that one. So who would like to draw this graph on the board? You guys know mathematics are going? This qualifies. What? Oh, no, no. So we put like 6 of these on the test and you're good to go, right? When all of a sudden revote, no exam, right? Revote. It's an awesome question. Like, cosecant is bad enough, but then we have pi over 6 to actually make it easier. Let's see what we can do with this. So first off, let's find the points where the break. Yes, you have a question?
No,
It's not? It's not continuous? Okay. All right. So we're going to start at first figuring out the graphs, and then once we have the graphs, we will take care of the rest. So I'm going to superimpose both graphs on top of each other and then erase those graphs in the regions where we don't need them. So you cannot have both graphs running over each other at all times because that would ruin the idea of a function. So they can only be to the side of each other. If you have issues with this, go find my stream in Precalculus 1 that I did last week on piecewise functions, and watch that part on how to graph and how to deal with piecewise functions. Now this one, as the added headache, has the cosecant. So let's see. I'm going to draw axes, and I see that I need y equals 2. So that's easy. Maybe I should do red and let's go with the blue and red. So let me go. This one is going to be red and the other one is going to be blue. So let's go with red. How do you graph cosecant? You graph cosecant by actually graphing sine and then flipping it inside out. Cosecant is 1 over sine. So if you draw sine, you just cut down the middle and you flip the cups outside. It's the fastest way. So we are actually dealing with a sine of pi x over 6. Where is the starting point for the sine? Since there is no c which moves things left and right, this sine must start at 0. And then we have to compute the period to see where the sine is going to end. So the period was 2 pi over b, and b in our case is pi over 6. So it appears that the whole thing is 12, right? Pi's will cancel, 6 goes upstairs, 6 times 2 is 12. So it appears that this sine will end at 12. So I'm going to call these 2 units each. So I'm going to call this 12. Halfway for the sine. Observe that there is no amplitude change, which means the amplitude is going to be 1. Actually, I'm not going to use 2 squares. Let's use the whole thing. So 6, 7, 8, 9. I can because it's 12. It's not that far. So we know that we are going to have at 1 and at -1. Now I am going to use the dashed line because this is not the graph. Remember, we are constructing the graph. So this is the sine. No negatives, which means it's not flipped or anything like that. So all good. Now that we have this, every time when sine hits the x-axis, means that the value for the sine, the y value for the sine is 0. But because cosecant is 1 over sine and 0 is in the denominator, that's where the vertical asymptotes appear. So vertical asymptotes will appear at every point where sine hits 0. For secant, everywhere where cosine hits 0. So I have vertical asymptotes everywhere. And now all I need to do is to invert the cups. So it's going to look like this. So this is the cosecant of 6 pi pi x over 6. You may choose to erase everything else. And now the blue line is this line, which is y equals to 2, and that's going to go forever, so that's the blue one. So we have a red graph and the blue graph. The problem is they're on top of each other, which means that this is not a function until I erase portions of the graph where they're not supposed to be. Yes? Uh-huh. Oh, perfect. So you are telling me that the cosecant, I should keep it between 1 and 5 and erase it everywhere else. Okay. So, perfect. So how did you get that? You just did it in your head. Yes. Okay. Yeah, but how do you know which values to pick? We start with -2 less equal than x minus 3 less equal than 2. And then we add 3 everywhere. So 1 less or equal than x less equal than 5. This is algebra. So distant in the past. Long forgotten. Which is creeping back in, right? So we are supposed to keep, so this one over here says keep cosecant between 1 and 5. So keep cosecant between 1 and 5. I'm going to go into my eraser here. And 1 and 5, keep this one. So after 5, I got to get rid of it. So this is gone. After 1, which is this one, is gone. And then the entire thing here is gone forever. Don't need any of those. And obviously the rest has to be the blue line, which means we are getting rid of the blue line here. So this could be continuous, right? If you really zoom in, because you can't draw this perfectly precise, but if you zoom in, it kind of, I missed it. But maybe could be continuous. So we're just going to do our calculations with limits and stuff so we know exactly what's happening here. So, number 1, does f of a exist? We have to compute at 1 and 5. How much is the cosecant of pi times 1 over 6? Because you are plugging in value 1 first. So how much is it? Well, it's the cosecant of pi over 6, which is the same as 1 over sine of pi over 6, which is 1 over 1/2, which is 2. If you divide $1 into two $50 coins, you have 2 of those coins. Awesome. But we also have to check for the cosecant at 5, so pi times 5 over 6, which is cosecant of 5 pi over 6, which is 1 over sine of 5 pi over 6, which is again the same situation, and you again get 2. So f of a exists. F of a exists. Problem 2. Not problem 2, sorry, the step 2. Limit. We've got to do 4 limits here. Actually, well, we don't, because the limit from the left and limit from the right for both of those will be just 2, so we don't have to worry about it. How much is the limit of pi x over 6? Cosecant, I forgot cosecant. Cosecant pi x over 6 as x approaches 1. In this case from the right, but it doesn't matter. It's 2. Just plug in basic limit. And what's the limit as x approaches 1 plus of 2? Well, sorry, 1 minus. What is it? Here's 2. So both of these are telling me that the limit as x approaches 1 of the function is 2. Awesome. But we also have to find the limit as x approaches 5 from the left. 5 from the left, it's going to be cosecant of pi x over 6, which is cosecant of 5 pi over 6, which is how much? 2. And the last one, limit x goes to 5 plus of 2 is 2. So all limits are 2, which means we have the limit part established. They all exist. And then number 3, well, 2 is equal to 2 because we got the 2 for number 1. We got the 2. And then for number 2, we got 2. So since 2 equals to 2, function is continuous. Now I can sense a little bit of a disturbance of the force over there when I started taking these limits, so we have to talk a little bit about this stuff. So, looking at this larger version of the graph, so these actually do meet nicely here and nicely there, so there is no interruption. Alright, so guys, let's take a look at this real quick. You have over here the cosecant function, and you have over here y equals to 2. It's a function. Guys, it's a function. Y equals to 2 is a function. There are no x's there because it's a horizontal line, so you have nowhere to plug any x. But it's still a function. So now, when we are dealing with the limit and we want to know whether the limit exists, well, since we have 2 problem values, one is at 1 and one is at 5, we have to do 2 limits, a limit for 1 and a limit for 5. Now the limits are done by performing 2 one-sided limits, and that's why we did 4 limits. So looking at 1, you have the approach from the left, which is x goes to 1 minus, and there is along line 2, obviously the answer is always 2 because it's a constant value 2. When you approach from the right, you're going to climb into this one, so this would be the cosecant, right, of pi x over 6, and you take the limit as that goes to 1, it worked out to be 2. Then another set of 2 limits for the other point, one for the left, one for the right. They also worked out to be 2. So now you have the limit here is 2, which matches the functional value, which was 2. So they're the same, it's continuous on this part. Here, the same situation. continuous on the part, and continuous on the part because at that point, because of that limit is the same as the function value. Got it. Questions, concerns about this? Yeah, you gotta go home and meditate on this and then see how it works later. Sure. Scroll down real quick. There you go. That was a real quick. Want it slower? You will. Let's do one more problem and then we're going to define more stuff. Now this problem is going to be a little bit backwards, but you got this. Find A such that f of x is continuous at A, at x equals A, whatever. So figure out which value A needs to have. 30 million, negative 0.2. Find the value for A so that function is continuous. You have two different functions. You need to connect. But tell anything you will immediately just go. I already said you need to fit two functions match up.
Oh, wait. So what is the A that's matched up?
Done? You guys are partying, so it's done?
Yeah, we're partying.
No. Oh, it is? Oh, okay, great. Yeah, I didn't know. That's my third step. You don't do step one. Oh, you don't? But that's what I did. I just like kind of I created like a framework and then I just remember there. Which means that you're understanding concept, which is good. Okay.
Wait, why don't you have to go to three?
Because I am telling you that the function should be continuous.
Ah.
So you're not checking if it is continuous.
Or just want the answer of that.
Yes. To be continuous, so you're looking for which A will make just the second step work out. Because the first step and the third step are kind of implied already. So just looking for the. Alright, so guys, if you haven't figured out so far, the only thing you need to do here is to make the second step work. Because the first step obviously holds because you have x cubed and a 2. It's going to be 8. And the third step is implied already because I am looking for the continuous function. So I know that the step 3 will hold. Step 1 already holds. So the only thing that we need to work with is the second step. So if you write out the second step, you plug in values, you're done. The second step says that the limit of the function, now from the left, which means x approaches 2 minus, which is x cubed, needs to be the same as the limit as x approaches 2 plus, which is ax squared. So once you solve this equation, you're done. Now what is your x? How much is x? X is 3. Very good. No, sorry, 2. So you have 2 cubed is equal to a times 2 squared, from where a is 2. Done. So if a is 2, you're going to have the limits to match up, and you will have the limits immediately to match up, because you can see that 2 cubed is the same as 2 times 2 squared. Both are 8. And then one of those 8s came from the calculation of the first one. So we have. Now we're going to define global continuity. Now that we know how to find continuous functions and maybe even how to fix them to be continuous, as you can see, now we want to define the global continuity. Unfortunately, we'll not have time today for 2.7. We're just going to move 2.7 and 3.1 for the next class. We only have 2 minutes left and then another 5 after that. So we are going to look at the global continuity now, and we're just going to say that the function is globally continuous if it's continuous at every point. which means you have to do infinitely many of these 1, 2, 3, 1, 2, 3, 1, 2, 3, right? If you want to check every point. But we know that's not possible, so we have different theorems to support it. So, another theorem. Function f of x is globally continuous if it is continuous at every point in its domain. Now, something like this is, wow, you're going to go and compute the continuity at every single point from negative infinity to positive infinity or whatever the domain is. And then once you have those calculations, you can claim the global continuity. Sheesh, right? So instead of doing that, we learn a theorem. And a theorem says all polynomial functions, exponential functions, square root functions, logarithmic functions, sine and cosine functions are continuous on their domains. That's a theorem. You get to use it. And then you don't have to go and prove every time when you need to use them. You can just call upon the theorem. So, another theorem that helps us solve problems says all polynomial, exponential, logarithmic, sine, cosine, radical, rationals are not continuous. What else? I think I covered everything. Or the functions that you covered in class. Are continuous on their respective domains. So here's the cool example where you can use this. Oh, and there's also another theorem. I mentioned the properties. Of continuous functions. So if f of x and g of x are continuous, then number one, f plus g, f minus g, cf, fg, f divided by g with g different than 0. F to some exponent of n. F of g of x and g of f of x are are all continuous. Now this comes in handy when you have a crazy problem that has multiple parts. So say you have a function f of x which says sine pi x minus open parenthesis x squared minus 3 plus 1, you know what, everything to the fourth power, who cares, divided by 10e to the x. And the question is this continuous? Your immediate response should be yes. Why? Yep. E to the x can never be 0, and because e to the x can never be 0, you can never have 0 in the denominator. So we know that sine is continuous, polynomials are continuous, e to the x is continuous, so they're all continuous. But the denominator cannot produce 0 in this case. And because the denominator cannot produce 0, then it's going to remain continuous. We are adding and subtracting and dividing and multiplying continuous functions here. And any combination of those continuous functions is still a continuous function unless you do division where the denominator ends up being 0. Some cases that's possible, in some cases not. So e to the x is a good one to remember, but you can also run into, let's say, x squared plus 1. X squared plus 1 can never be 0. Because any value you plug in for x and square it, it's going to be a positive number, you add 1 to it, right? So x squared plus 1 can never be 0. That's another good denominator for continuity. So the answer over here is yes, because e to the x cannot be 0, and all other functions. Now guys, I can cut and paste this question and replace sine with tangent. Aha. Right? Tangent comes in with its own discontinuities, which would propagate to the problem. If you have a tangent here, it guarantees that you cannot use 1 over 2 pi as the answer, because pi and pi will cancel, right? Oh, 2 pi squared. Sorry, 1/2. Guarantees that 1/2 would not work. Discontinuously 1/2. So if I replace this sine function, if I replace the sine function with any other function that is discontinuous, which is technically any of those 4, tangent, cotangent, secant, and cosecant, they are all discontinuous somewhere. And that will ruin the global continuity for the entire problem. If I have a single x in the denominator, immediately it kills it, right? Because that could be 0. So e to the x is a cool one because it can never be 0. X squared plus 1 is cool one. X to the 4th plus 1 or plus 3 is cool one. Again, cannot be 0. But many other functions can be 0. If you just have x plus 3, clearly, right? Negative 3 is the issue. So calculus is not memorizing problem by problem, procedure by procedure. Learn the theory. Those 3 statements up there are combined together to do the analysis. And this over here, the solution for this problem, is writing a paragraph, words, right? That's how you answer the question. You state in words. I don't have time now because we're already negative 2 minutes into the class. You start as a paragraph and you write, sine function is continuous on its entire domain. Polynomial functions are continuous on its own domain. The exponents on the polynomial functions are continuous as well. Exponential functions are continuous. So you are dealing with 100% continuous. You write this, it's already, 3 lines of text. when you write all of these, that each one of these is individually continuous. Then you say, in the same paragraph, that you are dividing by e to the x, which can never be 0, which will not involve any discontinuities, because the denominator can never be 0. Therefore, that function is globally continuous on its entire domain. Now, you can go on and argue that the entire domain in this particular case is negative infinity to positive infinity, so you can add that as well. You know, that's like the boss mode, right? Boss mode engaged. But that also shows up, you know, because you can have ln x. Ln x is another one, right? It can be 0, but it has restricted domain. So I can have ln x here, and then everything is going to be globally continuous. It's cool, whatever the line looks like, it's going to be globally continuous, but your domain is no longer negative infinity to positive infinity. The domain is 0 to infinity because you have ln x there. So you have to be careful. There is a piece about domains, piece about restricted domains, piece about, you know, what can be 0, what can be 0. You put them all together, but that all is after you learn the theory on top. There's also one more part of this lecture. We'll take care of that last part on next Saturday. So for next Saturday, we will finish 2.6. The intermediate value theorem is left, so we'll deal with that first thing. Then we'll talk about 2.7, precise definition of a limit. And then we are going to do 3.1, which is how to find derivatives and what it means using limits, which is technically 2.3 calculations. Then we're going to have review for the exam, and we're going to have the lab time, which means that all of you will download the labs. You can read off of the screen and do them in your notebook, or you can print them right away. You can stay now after class and, oh no, you can't because I didn't upload yet. Let me just end the stream. So just make sure you guys